Okay, all right. Shall we get started? Yeah. Okay. Yes. Okay. I hope today's session will be in within 1 hour or 1.5. We are preparing something for a long journey. From the from very simplest protocol all the way to the modern proving system. If we could do that, I don't know. I'm not quite sure if you could follow this trip. I'm not sure. I'm not quite sure right now. It depends. And Hood, yesterday we talked about that. We can just try to see how far we can go. So this morning I came up with the first part of our journey. The first will be a quick warm up. We'll introduce Schnorr identification protocol, which is a textbook protocol, but make sure everybody can understand it. There'll be the start of the all the way to the modern proving system. I'll have to understand that completely, and then we some basic concepts about what is commitments and especially on Peterson commitment, kind of another textbook protocol. And then we trying to batch, for example, for a prover, if he want to prove for multiple instances, how can we combine them together to just make them fit into one protocol and to do more efficient proving. And then we will go to the how can we prove a product. So that means that if we can prove product and multiplication and addition, that means we can prove a circuit, because an arithmetic circuit composed of are composed of two types of gates: additive gates and a multiplicative gate. And then we can prove a circuit if we get the power that we know how to prove a product. Then we want to do more efficiently using the vector commitment. So that means we can commit a vector that can be large, can be more than 1 million. And then we do more than product. We do something about prove something about the inner product. Inner product kind of two. It's a concept, mathematical concept from linear algebra. It's a simple, right? Basically, we have two very long vector. And we'll prove that the inner product of two vector or dot product of it is correct or not. And then if we can prove inner products, then that means we can do a polynomial commitment, because polynomial actually is the inner product of a coefficient vector and a monomial vector. So so only the first part of our journey. So at the end, the first stop, we will know how to prove a polynomial commitment, even if not so efficient, but it's efficient enough to build something. Okay. If you have any question, please stop me to make sure that you can follow. So the good news is that today we'll have math, but the math is simple. Okay, trust me, it's simple. It's a high school math. Okay. So wait a minute. Yeah, here. I think I cannot enlarge that screen. I think it's okay. Okay. A warm up. Schnorr ID protocol. So now we have two roles, a prover and the verifier. The prover, so which is what the statement is that prover want to prove that she, okay, that's prover be a female, a woman, a girl, like Alice, and the verifier, we call him Bob, okay, Alice Bob. And the prover, Alice, has a knowledge, so something a secret. For example, use the word the key. The key is a number from a field, a P. Okay, P is a finite field. It's a finite field. That means it probably is an integer between 0 and P minus 1. But the P is considerable large. It's very large. So K is a knowledge. The prover want to prove that, okay, I have a K, but I don't want to reveal to the verifier, reveal to Bob. So in the realistic applications, K can be a private key. In some applications, it's a private key. Okay. Okay. Here I just use a private key, but for more advanced proving system, key can be any witness of secrets. But here, because Schnorr protocol is an identification protocol, so it's a private key. And okay, what is the public key associated to with the private key? So we have a small key and a capital key. Okay, capital key is a public key. So now we introduce some math, but very simple. Okay, we can use it as a black box. I'll just write it like this. We use the square brackets. Okay, is that clear? Is that clear? You can see it? Okay, thank you. So, okay, what is a square bracket? Square bracket is small key. Here we introduce elliptic curve. So actually, traditionally we have different approaches to make the square brackets. The first one we can introduce a group generator. We just put I don't know how to say in English, G2K or something. It's a exponent of G. Power, yeah. Thank you very much. The power of key power of G, right? Yeah. Here G is a generator. Of a multiplicative group of some finite field. But in practice, the size of the group should be very large. So it's not impractical in reality. So that's why we always use the elliptic curve. The elliptic curve is it's advanced math. We cannot go deep into it. So, but it has the similar algebraic structure with the multiplicative group of finite field. It's also the group. As group, there's a cyclical group. So here we can introduce a generator. We call it capital G. And we just do a scalar multiplication, small key, dot capital G, to make sure that we put G into a box. Sorry, put the key, small key, into a box. And both of the two cases, if we don't know that small key, we cannot compute key out of the box. That means for any Bob, so if Bob knows power key of the key power of G, and Bob cannot calculate the get result of small key. It's called the discrete log problem. It's a hard problem if the order of our multiplicative group is very large. For the curve is similar, and we got this point. This point is point on elliptic curve. For example, equal to h for some h. Then, if Bob knows h, Bob cannot calculate small k. If Bob's computational resources can be limited. It's an assumption. The elliptic curve should be large enough. So, for example, we have some, the ZKP 256 K1 used by Bitcoin, or BN 254 used by Ethereum. Yeah, there's many, or BOS 12-3881. So there are many safe elliptic curves that we can use. But for simplicity, we just remember that if we put the small k into a black box, now small k will be safe. Then nobody can extract the value out of the box. It's safe. It's protected by a cryptographic assumption. But the assumption will be not safe by, if a quantum computer come out. It's not safe in the future, but right now it's okay. It's safe. Let's come back to the protocol. So here, small key is the private key, and the capital key is the public key. It's another public key. So before the protocol, we assume that Bob already knows the public key of Alice. So that means the key for verifier, Bob, he got key, okay, capital key, okay. Now the Alice is going to prove that, okay, I am Alice. Why? Because I has a private key which is according to the public key that everybody knows. So that's why, that's the reason that Schnorr protocol is called identification protocol, used for identification. So, okay, the first step of the protocol is that the Alice does care about the private key. It's not unknown to Bob during the protocol. So Alice will, as the first step, Alice will generate a R is also a random number, randomness, to protect the private key. You know. So as the first step of the protocol, the Alice put R into the box. That we use the capital R, capital R, to specify the black box with the randomness inside. So first step, the Alice just sends R, the capital R, to verifier, to Bob. The Bob cannot get this small r out of the black box. Okay. Yeah, that comes the second step. The verifier will challenge, just as the three coloring problem that we talked about yesterday. For example, a challenger C. C is a there's a toss coin by Bob and got a random number C, small c, and sent it back to reply to Alice. Okay, the third step, the Alice will send a number Z equals to R plus C dot key. So send the Z to verifier. Okay, here's the thing. Okay, Z, we can see Z as an encrypted message of key, right? We just view as the R as a one-time temporal symmetric key to protect small k, right? So if the Alice, if the Bob gets Z, if the Bob doesn't know R, the Bob cannot calculate or compute K, right? R is also in the black box. Okay, the assumption is that the Bob cannot extract the value out of a black box. Okay, but the verifier, the Bob even Bob doesn't know the exact value of both small k and both and small r, Bob can also verify the relationship between r and k. So that's the amazing fact that why we use group, we use elliptic curve or multiplicative group of finite field. The verifier will verify, okay, this is a final step. The verifier will verify if Alice knows the small k. So Bob will put Z into a black box, and check if R plus C dot K. And the right hand side of this equation also equals to, we just expand the definition. Okay. So the verifier just verify this equation to make sure that, okay, Alice has the private key. Okay, here's something that I don't mention. It's about the so-called additive homomorphism. Trust me, it's a high school math. Okay. Even the black box is black box, but still we have additional properties of black box. Is that so-called additive homomorphism? So let me explain that the additive homomorphism is a terminology from abstract algebra, but don't worry, it's very easy to understand. Homomorphism. And the black box has the following property that for any A plus B inside the black box will always equal to A plus B in the black box. Okay. With this property, this very useful property, the verifier can blindly verify the additive properties of some numbers, even they have already put into black box. Okay, got it. So. And we also have another like a vector space. If you have even know of algebra, that for a constant A, we can also have that. Okay. Also there's two properties. If we have this one, we will get this one. Okay. C is okay. A warning. We don't have the rigorous mathematical definition here. Just to make sure everybody get the intuition instead of. Otherwise, we'll fall into very math part. Okay, because we have the additive homomorphism, then the verifier can verify this equation without any knowledge of the value inside the black box, because we put the value into the black box can be added, and or do a scalar multiplication. We add multiple black poles together to get something. Yeah, so so take a look at this equation. Okay, it's the algebraic structure kind of identical, right? But here the verifier cannot get anything from the black box. So it's safe for Alice, right? It's safe for Alice. Okay. Let's stop here for 2 minutes for questions. So how can we trust that protocol is safe? So any ideas about why the protocol is correct? How can we prove that? It looks very simple, right? Okay, I encourage you to try to attack this protocol. So, okay,
so I have a lot of steps, interactions that I have to do with the prover and the verifier. And me as a prover, I know which steps the verifier is taking, so I know which variable he's gonna be able to sum up with those boxes. Like in the first occasion, we passed solidly the R. Right, the randomness at first, and in those interactions, how can he know the randomness at the second shot? It's because he knew on the first one, right? Those states are being saved during the entire verification of those iterations.
Sorry. Okay. Could you repeat that?
Sorry.
I'm sorry.
So in the first one, we are passing
first step, right? Here?
Yeah, the randomness.
Okay.
The
randomness, okay.
So the verifier can access this first step
in
future steps.
Okay. So this R is a one-time randomness. For a second round, for example, the Alice want to prove the second time, the Alice should use another R. So Alice cannot reuse R. Okay. It's definitely forbidden.
Okay, so this is not steps. Like I thought, like the R going further, like a first interaction, and then
just
response, and then later on we have the second interaction.
No. Just like different from a three coloring problem. That's just the 3 steps. That's all.
3 interactions.
It's 3 interactions. Yeah.
3 steps in a single interaction.
Yes, just a single protocol, single identification. So after the third steps, identification complete. So it doesn't looks like the 3 coloring problem.
To prove that you have the private key, you follow those steps.
Okay, no, yeah, I understand the context. I'm trying to understand.
But if you want to prove again, you repeat those steps with another random.
Yeah.
Yes. Okay. Yeah, that's clear. I'm just thinking like, how can he verify if I'm already passing like the hash, which is the C multiplied by K plus the randomness. Like I can try a lot of different randomness. How can I relate all the resulting hashes so that the verifier can say like you are correct?
Because of the warmupism, you're just guessing C or K. Because what? You're just guessing C or K. You're not guessing R. Because that's the one that you pass. You don't have to guess the range.
Yes, that was my first question. So he already knows R.
Yeah.
Yes, that was my question. How he already knows R.
Yes.
No.
The first step is equal to
the Bob cannot know small r. Just the capital R. Capital R is random. It's also random, right? So if Bob knows of a small r, Bob will get the private key of Alice. That'll be.
But isn't the purpose of like proving that you know the private key?
Sorry. Could we speak slower?
Isn't what Bob wants to verify that Alice knows the private key?
Yeah.
So how can he know that private key without actually like knowing the source of randomness to prove the hash is correct?
Oh, sorry, I can't get your question. So,
Because you hash everything.
Yeah, you hash everything.
But you have the homomorphic property. So he can know that the hash of the sum is the same as the sum of the hashes.
Okay. I guess I skipped basic math. I need to see some. I think I need to see some gold.
okay.
I need to see the logic from step by step, but yeah, it's hard to picture it.
Okay, so which
I see
point?
a lot of steps, but I don't understand like an actual step by step. I don't feel like this is first stage, this is second stage. Like
Okay.
It's very abstract. Like I like to the whole equation step by step.
Okay.
That to make it easy.
Okay. Probably we can. Okay, just we
Like try to
rerun.
debug the system. Like I'm trying to debug the system.
Okay. I think we will understand that after we trying to prove that the correctness of the protocol. That will be clear.
Sorry?
I think you'll be understand that after you know that we how to prove that the correctness of the protocol.
Okay.
Yeah, right now just memorize the steps.
Okay.
All right. So you're saying that this is broken, though? Right? Do you want to prove that it's broken?
No, it's correct. It's sound. But if you want to understand why this works, you have to try your best to try to attack that, and you will fail, and you will probably get more information, more intuition about that protocol.
Yes, it's the same thing we've done yesterday, but just with a mathematical explanation.
Yes, very similar to the recurrent problem, but some theoretical differences, but don't care about those stuff. It looks very similar, yeah.
Similar, but just more mathematical.
Yeah, yes. We will go deep into it instead of just three coloring the game. Okay.
I do kind of agree that you could like add numbers to different steps.
Okay.
You know, like you could just like add like little numbers to each step in the order that they happen. That would
Okay.
I think it's like each like equation and like
Okay, this is the first step. Is there randomness? Yes. The second step, put into a box and send to the verifier. Okay, this third step. C got the randomness. Got the randomness C. Bob got the new randomness C. Okay, it's just still randomness. But the randomness from the okay. Wait. Yeah, see the randomness generated by verifier, by Bob. And then Bob sent the randomness to the prover. Yeah, that's the first step. The prover will compute a Z, an encrypted private key, and send the Z back to the verifier. Okay, it's done. Then verifier will check the verify, do the final verification equation to check if. Sorry.
This small key is the private key, yeah?
Yes,
The big key is the public key
the
and
public key, yeah.
yeah. The small r is randomness.
Yeah,
and,
randomness.
And the great one is the capital R.
Oh, yeah. Capital R is we put the small r into a box to protect.
Call it a box.
Okay,
We actually call it a box.
Sorry?
It's actually called a box.
Yeah, we just call it a box.
What? The cardio box.
Sorry, car?
How in box.
Okay, we call it box. Okay.
Call it a box.
Call it a box.
I'm sorry.
Ok, vai ter. Ah, mas ó, aí falando dele, dá pra fazer associação que. Tipo,
I think a lot of people are trying to.
yes, we can say that it's similar, yeah, the process of public key to private key and randomness to R. And we have five steps. Five steps. We can show the same thing like I don't know why is this only one element and in additive homomorphism we had some A plus B.
We have multiple.
Sorry?
Z igual sorry. Z is equal to R plus
Capital R. You mean in the right hand side here? Or?
And the last line we had the explanation of additive homomorphism. Yeah?
Yes.
I'm trying to correlate with the Z.
Here we will, yeah, just yes. Sorry?
The lecture stopped? Or?
No. Just just stop for 5 minutes. Everybody to trying to attack the protocol. Okay. Here I finish this one. R plus. Yeah, any question?
So let's say like this. So after during the setup step, the public key should be sent to the verifier, right?
Sorry, public key.
The public key should be sent to verifier.
Yeah. Yeah, before the protocol. Yeah.
So for the step after sending the charges, the C is the real proof that was generated by prover in order to verify.
You mean R, small R?
Okay.
R or C? I don't get your question.
The step. Okay. That's the
Z. Okay, yeah, Z.
Z. Okay.
Okay.
Yeah. So that C is the real proof that was being sent to verifier in order to prove that it is really valid.
Yeah.
So, and another question is the source of proving. There are R and C that was being sent before verification. how does R and C was come?
C.
Yes. Now
C.
you see at R, that is randomness.
Yeah, R random is generated by prover and C generated by verifier.
So these these two are random numbers. But
Sorry?
let's say that these two are random numbers.
Yeah, two randomness. Yes.
But the method is any just make it random.
Yeah, make it random. And a small r is used for privacy protection because the Alice doesn't want to the Bob know the get the private key. But randomness from the Bob verifier is used for challenge to make sure that the Alice is honest. So there are two. Both sides will use the randomness, but for different purpose.
So the one is for the prover, for the randomness of prover side is for just to random the. I know that these two parts are random itself.
Yeah.
To make sure that these two parties are honest.
Yeah. Yes.
That is the point.
Yeah. Correct.
And the big R is technically an offset.
Okay.
There are many numbers of it.
Yeah.
But prover at one time of proving.
Yeah.
We just pick one.
Yeah.
And it technically can be proven like many times or different
Yeah.
as long as it is correct.
Yeah.
So technically, at last, if we prove like 100 times, it will be probability, and it should be like.
Yeah, okay, just the one round, just the one.
But for one round, I think I can for one round. But I've heard that in implementation, what is very unique is like if we prove like many multiple times.
Okay, just the one time.
Yeah.
Approve just the one time. Just the one time. Okay, yesterday for 3 coloring, we have to. The verifier have to challenge multiple times to make sure the possibilities, his confidence can be high. But for this protocol, the verifier only challenge only once. That's enough. That's the difference.
So it's up to what kind of problem we are tackling.
Sorry?
So it's up to what kind of problem we're tackling.
Yeah.
Following problem it has many sets of the.
Okay. It's according to the protocol design.
This one is a part, it's subset.
Yeah, this one is just the one time challenge. 3 coloring protocol is easy to understand, but the verifier has to be multiple challenge. Okay. Okay, it's there. Okay.
We use now this one is correlated to that.
Yeah, we can draw this connection by using this one because it's similar to, for example, A0 plus A1 plus AN equals, no, the same. There are equals to A plus A and equals to N times A. Right? Okay, this.
Okay.
The same equation.
This is like the N.
Okay, well here you see it's
I know that it's part of the hash. I know that it's part of the hash, and I know that R and C were previously existed, so I can
All right. Let's go back to the session. Hello. Okay.
Okay, this is afterwards.
Okay. Yeah, here I wrote down some, the equation here, you can get the completeness of the protocol. So if Alice is honest, then then she must be passed. They must pass the verification verification step. Okay. And also the additive homomorphism is important. The property is very important because the homomorphism property supports that the equation holds, right? Okay, is that clear? Okay, probably okay.
No, just because we also talked. I think everyone just talked about this. I think for me, the additive homomorphism is just a very complicated word for something that is fairly simple, right? It's basically if you have the non-hash version of A and B, like lower A and lower B is the non-hash version of A and B. If you hash that, you go to the hash version of A and B separately.
It's not hash.
Like for me, what do you mean it's not hash? Like for me, if it's in the brackets, it's hash.
It's not hash. it's not hash. We will use different technologies, but
okay,
not
so
hash.
What do you call it?
Peterson commitment, and we will talk it later.
Sure, okay.
It's not hash.
But
or to put it onto a elliptic curve, then we will get the property.
All these words, they are very. But yeah, it's a very simple concept, but the word for it is very complicated. Like it seems complicated.
Yeah. Yes.
Yeah.
It's true. Okay. Okay, just now we are going to. Okay, the protocol is simple, but not easy to understand actually. Yeah. So then we're trying to prove why the protocol is correct. Why? I think okay. Please, if you have any question, just stop me. Okay, it will be not easy for beginners. So.
I'll save it for later.
So for many protocols, we have 3 different properties. Probably you already seen the properties, in some articles talking about the zero-knowledge proofs or the snarks. The first is completeness. A second is soundness. Sorry. A third one is called zero knowledge. Okay. Here we only prove the completeness. So what is completeness? Completeness saying that any honest prover always pass the verification. So if we are honest that okay, we already successfully prove that okay, you are the Alice. You are Alice. So completeness is about the honest prover. But soundness is on the other side, saying any dishonest prover cannot pass the verification. Oh, sorry?
Before we keep going, is homomorphic addition is related to variance and security?
Sorry? I can't hear you.
I have a question.
Uh-huh.
That
Okay, sorry.
is homomorphic addition related to variance and elliptic curve?
Pairing?
Variance.
Oh, no pairing.
No, this is not the same as variance. Homomorphic addition is not related with variance.
No, not related to tightly related to pairings, because pairing. Okay, we'll talk about pairing when we arrive at the KZG10 commitment.
Okay.
Here we just use discrete log. That we just use elliptic curve, any elliptic curve, and then And some kernels are parent friendly. They will have efficient parent operations, but generally on, for example, ZKP 256 K1, the curve, the parent operation cannot be very, very efficient. But here there is a parent, but okay, that's different. It's different. Another topic.
Yeah.
Okay.
But that terms are encrypted. You encrypt A plus B is equal to the encryption of A plus encryption of B.
Yeah.
Okay. Yeah.
Yes. Yes. All right. Okay, Sun is saying that any dishonest prover cannot pass the verification. And the third property is saying that any verifier cannot get the private key. Okay. Now we are going to prove that. Okay, just not just I say something, trust me. Okay, we just trust the proof. We only trust proof. So now we're trying to prove the zero knowledge property at first, but zero knowledge part cannot be easier to prove. If we understand the proof, that we will go to the soundness part. Okay, we will introduce a very important concept. It's called simulation. Anyone heard of this word, simulation?
Matrix.
Raise your hand. Yeah, matrix. Yeah. In cryptography, simulation. Anybody used to know of this word? Please try. Yeah, I like. Anyone else? All right. So it will be, it's not easy to think it over, think it about, but it's very important. But actually, you understand it will be easy. Simulation, yeah, simulation just as a simulation in matrix, the same idea.
Score.
So yesterday we talked about knowledge. What is knowledge? What is proof? And we didn't talk about what is zero knowledge. So zero knowledge looks like a marketing word. Actually, it's not, because zero knowledge has its formal, rigorous definition. Defined by simulation, the idea. People call it the simulation paradigm. Okay, it's a great idea, a simulation to prove that the real world. Here is a simulated world, or okay, as in the Matrix, the movie, right? In the real world, every human being will get a PEP, connect our brain. In the simulated world, kind of built by code. And everybody seems like, okay, we are alive. Actually, it's not true, right? Because all we see, taste, and hear, all of the stuff are fake. And because they directly put the information into our mind, or we cannot realize that. Okay, this is the simulation idea. So, in the simulation world, kind of similar. And Bob, the verifier, is the poor boy that at his brain connected with some machine. Okay, here will come see a girl who names like Zelis, not Alice. Looks same. Okay. The Bob cannot distinguish between Alice or Zelis, or Bob cannot distinguish whether he's in dream or in the simulated world or in the physical world. And in Zelis, because Zelis is not Alice, so Zelis has no private key at all. Okay. So Alice will interact with Bob. You know, 3 steps for interaction. Alice want to prove that, okay, she is the Alice in another universe, another real world, you know. And in the real world, just the protocol almost same to identical to this interaction. So here, 3 steps. Alice, the left side, right? In the real world, Alice has the key, small key, the private key. But that is okay. She hasn't any private key information. So the proof about the zero knowledge saying if Alice without any private key can cheat Bob successfully, and Bob cannot distinguish whether he's in the simulated world or in the physical world, then the protocol is zero knowledge. Because in simulated world, there's no knowledge at all. But in real world, there's knowledge. Okay, here is knowledge. But here's no knowledge. Sorry, no knowledge at all. So it seems weird, right? Okay, it's intuitive that the protocol on the right-hand side is different from the protocol at the left. So we have to come up with a new protocol which can cheat Bob. Okay, how can we do that? You must be very curious about that. Okay. The problem is that if yesterday we talked about the one point we can attack the protocol is that if prover can predict the randomness, the challenge from the verifier, the prover could, cheat verifier. So suppose that Alice has some, superpower, can predict randomness. For example, Bob will in the future will get a challenge C prime. The randomness, but actually it's not. So Alice will know that C prime even before the protocol. Then Alice will prepare the protocol at this 3rd step to generate a Z prime, which is a random number, just the junk, any number. It's a random number, or it's junk, Z prime. So, okay, what will Alice send to Bob at the 1st step? Okay, the goal is that to cheat Bob. So let's analyze this equation that Bob will use in the future to check. Okay, so Bob will, let me write this, Z equals to R plus C prime capital K, right? So then we can Okay. Okay, let me first C2R. Okay, let me how to forge that. On the first step, the expression. So here's Z prime. Yeah. The Zelis will get this equation R equals to Z minus C prime dot K. Okay. R star, we'll get R star. So at the first step, Zelis will send R star. And Bob, as predicted, send a C prime. And Zelis will send a Z prime. Okay. Then Bob, okay, the R star, C prime, and Z prime will pass the Bob's verification for sure. Okay, just to stop here for 2 minutes or 5 minutes.
So in the simulator now, Zelis basically hacked, right? Like he sent junk and it passed.
Yeah.
So in the simulation, we basically try to see if she's able to do that, and in this case, she is. So that's good or bad? That's bad, right?
Yeah, it's bad, right?
Yeah.
Okay, it's
good because there's no knowledge. Yeah. But in the real world, they don't know that Alice can't predict the C prime. Yeah, so it means it's no knowledge. But in the real world, if Alice cannot know randomness, she can't fake the R star, right? Yeah. So I think it's good.
Okay. Yes. Yes. Good or bad? It depends. Depends on which side you stand, right? So okay, 5 minutes to think it over, and because the C prime is predictable, then Zelis can forge a R star, Yeah, let me confirm that. Okay, for sure we'll pass this. Okay. Z prime equals to R star plus C prime K equals to Z minus Z K plus C K equals to Z. Yeah.
How is Alice getting her thing?
Sorry?
What is Alice getting
Sorry?
out of this interaction? What is Alice getting out of this interaction?
Zelis or Alice?
Either one, yeah.
So now we are in the simulated world. There is no Alice. No Alice. Just
Zelis, yeah.
only Zelis.
What is the actual exchange with Bob?
Oh, exchange?
Exchange, yeah. Like what are they doing the cryptography exchange for?
Oh, I don't know what you are asking.
So like they are doing this proof with each other. Bob and Dallas are doing these proofs challenges with each other.
Oh, you mean we are in the simulated world, right? So why we run that protocol? Yeah, is that your question?
So, like, yeah, what are they interacting about? What would they be
Okay.
exchanging?
The purpose of Zalis is to pass the verification to prove that Zalis actually is Zalis, Alice, without any private key from Alice. It's kind of a attacking protocol, but in the simulated world. Yeah, okay. But that protocol actually is a proof. It's the proof to prove that their knowledge. Sorry?
So that it's a proof that Zalis can potentially be valid.
Yeah.
Consegue mandar lá e trazer. Porque ó, o coisinha é igual você mesmo. Aí tem o Z, tem o Z na equação igual. Você pegar a coisa ali no simulado, só no simulado saberia. Mas aí eu já falei com o computador aqui, tá quebrando interações, já construindo interações diretas, interação do time interação eu acho que aí que entra o depender da parte do talvez não consiga
Okay. Okay.
就是，但是这样的话，你怎么样能保证就是，如果在现实世界中它有一个 randomC 的话 ，Alice 它一定没有其他办法 fake 就造一个 Z 出来。
因为在现实世界中，鲍勃绝对不能让爱丽丝能知道这个随机数是什么。
对，我知道现实中他不会知道随机数，
那就造不出来，就造不出来。
肯定造不出来。
对，肯定造不出来。
OK。
肯定造不出来，我们接下来要证，现在还没弄。现在只是对争一边的。对。All right, let's go back. Let's back to the lecture. Okay. Now we have successfully proved the zero-knowledge property of the protocol. Okay. The proof is that the proof is the existence of the algorithm. The algorithm conducted by Zalis to fool Bob. Okay. Successfully cheat past the verification. So that's a proof. Actually, it's proof. Proof that the protocol in the real world is zero knowledge, because Bob cannot distinguish whether he's in the real world or simulated world. So then, in the real world, Bob cannot get zero knowledge from the interaction, right? Otherwise, we cannot construct Zalis here in the simulated world, right? Okay.
I mean, doesn't that mean that if you can't tell if he's in a simulated world, but we're trying to create these zero-knowledge proofs about our world?
Yeah.
Then aren't you saying that zero-knowledge proofs actually mean that we're less sure if we're in this world and not like proving more things about it?
Yeah. It's cool, right?
Yeah.
Yeah. Why is it zero knowledge? Because we could build a simulated world that we have no zero knowledge but can pass the verification. It's kind of attacking, but attacking is a proof to prove the security of the protocol in the real world. Okay, it sounds cool, right? It's a, I think it's a very great.
I came to learn math and I'm having an existential crisis.
Okay, so now the zero knowledge property, is used for Alice, right? Protect the private key is safe during the interaction. But on the other side, so how can we prove that a dishonest Alice cannot pass the verification? So we'll use simulation idea again to prove that the other side. Yeah. Let's build another simulated world to prove the soundness. Soundness saying that disprover, a dishonest Alice always failed. Okay. Okay. Oh, something I forgot to mention. How can we build the simulated world? So actually we, how to say in English, to give Zali some superpower. That's okay. It's a Turing computable privilege, not any. It's not a god. A god can do anything. So it's not a god. It's not a superpower. It's just okay. It has power to. Okay, no. That superpower should be programmed. It's a Turing saying that we can program the algorithm using programming languages. It's computable. It's efficiently computable. It's not okay.
And then superpower can also only be like one thing at a time, right? Like it cannot be two superpowers.
Yeah.
Otherwise, we don't really know.
Yeah. Yes. It's not a superpower. It's a superpower is not accurate word. Actually, here, how can we give Alice some power? This power can be realized in simulated world, but it's reasonable. So here, there's some approaches. One approach is easier to understand. Is time rewinding. That in simulated world, we can go back to the past. For example, 1 hour before or 1 year before. We can travel, time traveling, something like that. So that is why Zalice can predict the randomness of Bob, because Zalice can do time traveling, just like science fiction, describe. So the next question is that how can you do that on Turing machine to achieve time traveling? That the good news is that okay, we can do that because anybody can, we use the VMware, right? We take a snapshot of the operating system for some time, then we can reload the old snapshot. Literally, we go back to past and rerun the whole process. It also looks like we save the playing a video game. That will save the state, and we'll fill that the boss, and then we'll reload that, to play that again. So kind of something like that. So time rewinding is totally doable on Turing machine. So here we just imagine that here Zalice will blindly go the first step, and then get the randomness from Bob, then do a time traveling. But Bob cannot realize that. Okay. So time traveling is the magical point that the Bob cannot realize the time traveling at all. Otherwise, it's not a time traveling. So by using time traveling, Alice can predict the randomness. Okay, any question? Okay.
Why did you choose the Turing machine? Or why, what was its limitation? Really means.
Okay, Turing machine means that it's constructible. Yeah. Even in a simulated world, it's not a absurd world. You know, it's still be physical. It looks like put you into a video game. So it's the idea similar to the philosophical world simulation. It's the same, and also the same idea from the Matrix movie. You have to, even in the simulated world, you have to obey the physical rules. Yeah.
You mean actually you can't make something not equal to be equal? Is that
I don't know what you mean.
Like additive polymorphism is still law, even in the simulation. You cannot change.
Yes. Yeah.
So it's actually not exactly need to get Turing machine. It's just need to obey some law.
Yeah.
Okay.
But generally a Turing machine.
Okay.
Yeah, because in computer science or cryptography, we need that limitation that that has to be polynomial bounded computation resources. Yeah, you are right. Okay. So why time traveling? Because time traveling is so important in the following proving. Okay, again, we have a real world. And again, another different simulated world. But now, because we want to prove the soundness of the protocol, here as the Alice, we have Bob. But here in simulated world, Alice is the victim. We got another guy we called Bobby or something. He's the guy with the superpowers, you know, can rewind the time. So here the Alice will, the Alice as the victim cannot distinguish which world she is in. So in the first step, Alice will send R, the capital R, with the randomness inside. And then Bob will challenge with C0, a challenge number. Then Alice will send Z0. Z0 equals to R equals to, capital R equals to small r, black box, R plus C0 times K, right? Because Alice has a small key as private key. And now when Bobby got Z0, okay, the Bobby will conduct time traveling to the second step. The Bobby will send C1, another challenge. And Alice, because it's time traveling, Alice didn't realize that. So Alice will send another z1 to z1 equals to r plus c1 dot key to Bobby. Then Bobby will calculate the small key, the private key of Alice. Why? Because we have two equations, z0 equals to r plus c0 times k, and z1 equals to r plus c1 times k. I just do a subtraction. 0 minus c1 equals to c1 minus c0 minus c1 times k, and k equals to z0 minus z1 over c1 minus c1. Okay. So right now, yeah.
I'll answer it.
Yeah, the Bobby got the private key from Alice. So this is a proof. The existence of this algorithm successfully proved that the protocol is sound. Why? Otherwise, in the real world, if Alice has no private key, Bob will get nothing. So the algorithm does not exist at all. Okay.
And that's only possible because R is because R is the same for
Yes.
C0,
Yeah.
C1.
Yeah. Yes. R is reused.
Right.
Yeah. Okay. Let me stop here for 5 minutes. Okay.
I don't understand, like, why proving kind of like is not sound with time traveling prove something about the real world.
Sorry.
I don't understand why proving these things about the simulated world.
Mm?
We're proving kind of like in the simulated world is unsound. Or
Implies that the soundness of the real world, right?
Yeah. Before it's unsound and before here there is no zero knowledge. Seems how that proves something about the real world.
Okay. Okay.
Something with time traveling proves about the world without time traveling.
Okay. Okay, here's the point. If Alice, because it's the same Alice, right? Same Alice. If Alice has no key, no private key, this protocol, we cannot construct that protocol, right? Because Bobby will extract nothing. Because in simulated world, Bobby can successfully got the private key, got something out of it. Because the two worlds have the similar, the identical view. From the point of view from Alice's eyes, they are identical. So a dishonest Alice will always fail in simulated world. So the protocol will fail some step. Or we can say that the extractor algorithm does not exist.
Like if you write your own software, right, you run tests. And if you run a test, you replace the variable that's provided by the user with the variable that you provide yourself, right? To make the software run. And if the software runs successfully, your test ran correctly as well. So in a sense, you time traveled forward to replace a variable from a user by yourself. So you prove that it runs correctly by time traveling yourself because you write a test. You kind of know what I mean? Like, and that's a proof that your software works. And the same thing we do kind of feel like we replace something which we cannot know because we're in a different time, but now it actually, I don't know, like, so if your software is like addition, like A plus B equals C, right? You don't know what A and B is, but you time travel, so you know what A and B is. So you replace A with 1 and B with 2, and if the result is 3, your software works, right? Because you have replaced the variables with numbers that you wouldn't know unless the user tries to run your software. Does that kind of make sense? No, sorry.
I don't know, like, so what the test with function.
I guess if the simulation is a test. The simulation is a test
for
the program. Yeah, no, okay, sorry.
Okay, another point I should emphasize that because of the superpower, the time traveling cannot happen in the real world. Otherwise, the protocol is unsound. And in some the articles from the security guys, there was a famous vulnerability of Sony PlayStation 3 or PlayStation 3. And the developer put a constant as a randomness for a challenge. It's a constant. And the cracker, just noticed that, aware of that, a constant randomness. So the cracker just get the private key of Sony. So some guy published a article that saying, okay, this vulnerability of digital signature, okay, it's totally wrong. He's wrong because the vulnerability actually is the proof of the soundness. It's interesting. Okay. So design the protocol is kind of very dangerous, very dangerous. Okay, if put more restriction on the prover, if we unsound. If put too much restriction on the verifier, if we not zero knowledge. So design protocol is very dangerous. So it's a warning that you want to design the protocol for your specific application. You have to be, learn. You have to learn a lot of things about how to prove the security of protocols. You need to learn a lot. Otherwise, just follow the protocol on paper. Okay, it seems that we have 1.5 hours today. Basically we go through the soundness proof and zero proofs, the proof of the protocol. And this protocol is fairly simple that we can, I encourage you to think it over and trying to attack from different angles and trying to, We still have now have a channel, right? We can discuss a lot of stuff there. Yeah, okay.
Do we also prove completeness?
Yeah, okay, completeness is here. This is completeness proof. Because honest prover always pass the verification.
So the completeness proof is the protocol itself?
Yeah.
In 30 minutes, we will have the induction here. Okay, so we talk a bit about the problem generality.
Okay.
In 30 minutes, we will have the induction here. Induction.
什么？